Studies Section 5, Two-Variable Regression Model. Introduction. This section deals with the estimation of the population regression function on the basis of sample regression function. The method of estimation is the ordinary least square, OLS, which will be in terms of two-variable regression model. Learning outcomes. When you have studied this section, you should be able to evaluate the ordinary least square OLS method, derive the estimators of the OLS, discuss the properties of OLS estimator, derive the confidence interval of estimators. The method of ordinary least squares OLS. This method of regression analysis is propounded by a German mathematician called Carl Friedrich Gauss. In order to understand this method, let's begin by explaining the principle behind the least squares. Remember that in two-variable population regression function, as written below, but as noted earlier, this is not directly observable except through the sample regression function. In the equation below, where yi is the estimated conditional mean value of yi, this sample regression function is determined through the following equation below. This shows that mu I residuals are the differences between the actual and estimated y values given n pairs of observations on y and xi. The sample regression function will be determined in such a way that it will be close as possible to the actual y. To do this, the sample regression is selected such that the sum of the residuals summation mu I estimator is equal to summation into bracket y minus y estimator is as small as possible. The adoption of take 2. The adoption of least squares criterion would help to avoid some problems that are associated with the residuals. This states that the sample regression can be fixed in such way that the adoption of least squares criterion would help to avoid some problems that are associated with the residuals. This states that the sample regression can be fixed in such way that summation mu I squared is equal to summation into bracket yi minus yi estimator squared is equal to summation into bracket yi minus beta 1 estimator minus beta 2 estimator xi squared is as small as possible where mu I squared are the squared residuals. By squaring mu I estimator, this method gives more weight to residuals. In the least square procedure, the larger the mu I estimator in absolute value, the larger the summation mu I estimator squared. Another reason for the least squares method lies in the fact that the estimators obtained by it have some very desirable statistical properties. It could be deduced from equation 19 that summation mu I estimator squared is equal to f of brackets beta 1 estimator, beta 2 estimator, equation 20, which means that the sum of the squared residuals is some function of estimators beta 1 and beta 2. Thus, given different values for beta 1 and beta 2 will lead to different values for mu's estimator and hence different values of summation mu I estimator squared. Derivation of the OLS estimators. The dominant and powerful estimating principle that emerged in the early years of the 19th century is the least squares. The principle or method of least squares chooses beta 1 and beta 2 estimators in such a manner that for a given sample or set of data, the sum of square of the residual is as small as possible. That is, for any given sample, The method of least squares provides unique estimates of beta 1 estimator and beta 2 estimator that give the smallest possible value of summation mu I estimator squared. Let the residual from any fitted straight line be denoted by mu I is equal to yi minus yi estimator is equal to yi minus beta 1 estimator minus beta 2 estimator xi. I is equal to 1, 2, n, equation 21. Each pair of beta 1 estimator and beta 2 estimator values defines a different line and hence a different set of residuals. The residual sum of square is thus a function of beta 1 estimator and beta 2 estimator. The least squares principle is to select the beta 1 estimator and beta 2 estimator that would minimize the residual sum of squares, RSS. The equation RSS is written below. The necessary conditions for a stationary value of RSS are also written in equations below. Simplify gives the normal equations for the linear regression of y and x. That is, summation y is equal to n beta 1 estimator plus beta 2 estimator summation x, equation 24. Beta 1 estimator summation x plus beta 2 estimator summation x squared, equation 25, where n is the sample size. These simultaneous equations are known as the normal equations. The first normal equation may be rewritten as beta 1 estimator is equal to y bar minus beta 2 estimator x bar, equation 26. Substituting for beta 1 estimator in the second normal equation or solving the simultaneous equations 24 and 25 gives the equation below. Or it could be alternatively expressed as beta 2 estimator is equal to summation xy over summation x squared, equation 26b, which is in deviation form, where x bar and y bar are the sample means of x and y, and where x denotes xi minus x bar, while y is yi minus y bar. It could also be said that summation xy represents the numerator in equation 26a, while summation x squared represents the denominator in the same equation. The estimators that we got are the least squares estimators because they are derived from the least square principles. The principles are: 1. OLS estimators are expressed solely in terms of the observable quantities. 2. They are said to be point estimators, which means that they give points of single value of the relevant population parameter. 3. Since the OLS estimates are obtained from the sample data, the sample regression line can be obtained as below. The assumptions underlying the least squared method. The following are the assumptions underlying the use of least squared method, which is provided by the Gaussian classical linear regression model. This is the cornerstone of most econometric theory. 1. In linear regression model, the model is linear in the parameters, e.g., yi is equal to beta 1 plus beta 2 xi plus mu I. Note that the regressand y and the regressor x themselves may be nonlinear. 2. It is assumed that x values are fixed in repeated sampling. That is, the values taken by the regressor x are fixed in repeated samples. In other words, x is assumed to be non-stochastic. 3. The disturbance u is assumed to have zero mean value. That is, the mean or expected value of the random disturbance term ui is 0 given the value of xi. Symbolically, we have e into brackets mu I over xi is equal to 0, equation 27. 4. Least squares assumed homoscedasticity or equal variance of ui. That is, given the value of xi, the variance of ui is the same for all observations. The conditional variances of ui are identical. This could be expressed as shown in the equations below. Where VAR stands for variance. 5. There is no autocorrelation between the disturbances. Given any two xi and xj, I is not equal to j. The correlation between any two mu I and mu j, I is not equal to j, is 0. It could be written as shown below. Where I and j are two different observations and where COV indicates covariance. Equation 29 simply means that the disturbances mu I and mu j are uncorrelated and also indicate that there is no serial correlation or no autocorrelation. That is, given xi, the deviations of any two y values from their mean value do not show the patterns as those in figure 5.2a and 5.2b. Figure 5.2a shows that the mu's are positively correlated, that is, a positive u followed by another positive u, or a negative u followed by a negative u, while figure 3b indicates that mu's are negatively correlated. This means that a positive mu is followed by a negative mu and vice versa. Figure 5.2a and 5.2b are examples of the presence of autocorrelation or serial correlation. However, figure 5.2c shows that there are no systematic patterns of the disturbances, thus meaning that there is zero correlation or no autocorrelation. 6. The number of observations n must be greater than the number of parameters to be estimated. In other words, the number of observations n must be greater than the number of explanatory variables. 7. There must be variability in x values. The x values in a given sample must not all be the same. Technically, variance x must be a finite positive number. If all the x values are identical, then xi is equal to x bar. 8. The regression model is correctly specified. Alternatively, there is no specification, bias, or error in the model used in empirical analysis. The classical econometric methodology assumes implicitly, if not explicitly, that the model used to test an economic theory is correctly specified. An econometric investigation begins with the specification of the econometric model underlying the phenomenon of interest. Some issues arise from the specification of the model, the functional form, that is, where it is linear in parameters, variables, or both, and the kind of probability assumptions made about the yi, the xi, and the mu I in the model. 9. It is also assumed that there is no perfect multicollinearity. This means that there is no perfect linear relationship among the explanatory variables. Properties of OLS estimators, the Gauss-Markov theorem. Apart from the assumptions of OLS, there is also the property of the least squares estimate. It is in the Gauss-Markov theorem that these properties are found. It is the best linear unbiased property of an estimator that allows adequate understanding of the theorem. An estimator, say beta 2, is a best linear unbiased estimator of beta 2 if the following hold. 1. It is linear, which indicates there is a linear function of a random variable, such as the dependent variable y, in the regression model. 2. It must be unbiased such that an average or expected value E into bracket beta 2 estimator is equal to the true value beta 2. 3. There is minimum variance in the class of all such linear unbiased estimators, while an unbiased estimator with the least variance is known as efficient estimator. Further, in the context of any regression, it can be proved that the OLS estimators are blue, which is the main provision of the Gauss-Markov theorem. Coefficient of determination, goodness of fit. The coefficient of determination shows how well a regression line fits the data. If all the observations lie on the regression line, then it could be said that there is perfect goodness of fit, but this is often not the case. In reality, there is usually either positive μi estimator or negative μi estimator. The best of it is that the residuals that are around the regression line are as small as possible. Thus, the coefficient of determination denoted as R squared for two variable case of capital R squared for multiple regressions shows the extent to which a sample regression line fits the data. Let's compute R squared. Remember that yi is equal to yi estimator plus μi estimator, or in the deviation form, yi is equal to yi estimator plus μi estimator, equation 30. Squaring both sides and summing over the sample gives the equations below. Since summation yi estimator μi estimator is equal to 0, the different sum of square appearing in equation 31 are summation yi squared is equal to summation into bracket yi minus y bar squared, which is the total variation of the actual y values about their sample mean. This is called the total sum of square, TSS. Summation yi squared estimator is equal to summation yi estimator minus y bar into bracket squared is the explained sum of squares, ESS, while summation μi estimator squared is the residual or the unexplained variation of the y values about the regression line, which is called residual sum of squares, RSS. Therefore, TSS is equal to ESS plus RSS, equation 32. This means that the total variation in the observed y values about their mean value is attributed to the regression line and random forces, since not all actual y observations lie on the fitted line. This could be represented diagrammatically. Divide both sides of equation 32 by TSS. We give the equations below. Thus, the R squared measures the proportion or percentage of the total variation in y that is being explained by the regression model. Capital R squared has two properties. They are A, a non-negative quantity, and B, the limit of 0 less than or equal to R squared less than or equal to 1. If the R squared is 1, it means that there is perfect fit. That is, yi estimator is equal to yi for each I. However, if R squared is equal to 0, this means that there is no relationship between the dependent variable and the explanatory variable whatsoever. That is, beta 2 estimator is equal to 0. In this case, y estimator is equal to beta 1 estimator plus beta 2 estimator xi is equal to y bar minus beta 2 estimator xi bar into bracket plus beta 2 estimator xi, where beta 1 estimator is equal to y bar minus beta 2 estimator xi bar. Then y estimator is equal to y bar plus beta 2 estimator into bracket xi minus x bar bracket closed. Let's assume xi minus x bar in bracket is equal to 0. Then y estimator is equal to y bar. That is, the best prediction of any y value is simply its mean value. In this case, the regression line will be horizontal to the x-axis. The R-squared can also be obtained more easily from the following formula below. Dividing the numerator and the denominator by the sample size n or n minus 1. If the sample size is small, gives the equation 38 below, where x y squared and x squared are the simple variances of y and x respectively, based on the definition of R squared. It is possible to express ESS and RSS as follows. Therefore, TSS is equal to ESS plus RSS. Summation yi squared is equal to R squared summation yi squared plus y minus R squared into bracket summation yi squared. Equation 41. The normality assumption. The classical normal linear regression model. The two variable classical linear disturbances mu I are assumed here. This type of model is called the classical normal linear regression model, CNLRM. The OLS method does not make any assumption about the probabilistic nature of mu I, which makes it of little relevance for the purpose of drawing inferences about the population regression function from the sample regression function. This gap can be filled if assumption about the mu I can be made in line with some probabilistic distribution. Thus, it is usually assumed that the mu I follows the normal distribution. The classical normal linear regression assumes that each mu I is normally distributed with mean such that E into bracket mu I is equal to 0, equation 42. Variance such that E into bracket mu I squared is equal to standard deviation squared, equation 43. Covariance mu I mu j into bracket such that E into bracket mu I mu j is equal to 0. I is not equal to j, equation 44. Compressing this assumption gives mu I is distributed n into bracket 0 standard deviation squared, equation 45, where the sign means distributed as and n stands for normal distribution. The terms in the parentheses show the two parameters of the normal distribution, that is, mean and variance. Note that for two normally distributed variables, zero covariance or correlation means that both variables are independent. With the normality assumption in equation 44, this shows that mu I and mu j is uncorrelated and also distributed independently. Let us rewrite equation 45 as follows. Mu I is distributed on NID into bracket 0 standard deviation squared, equation 46, where NID indicate normally and independently distributed. The following are the reasons for assuming normality. A. The central limit theorem provides the theoretical justification for the normality assumption of mu I. This is due to the fact that the central limit theorem of statistics assumes that there are large numbers of independent and identically distributed random variables that, with a few exemptions, the distribution of their sum trends to a normal distribution as the number of such variables increases indefinitely. This is because The mu I represents the influence of all explanatory variables that are not explicitly considered in the regression model and influence are small or at least random. B. Even if the number of variables is not large and not strictly dependent, their sum can still be normally distributed. C. The normal distribution is a comparatively simple distribution that includes only two parameters, mean and variance. 3. The central limit theorem provides the theoretical justification for the normality assumption of mu I. This is due to the fact that the central limit theorem of statistics assumes that there are large numbers of independent and identically distributed random variables that, with a few exemptions, the distribution of their sum tends to a normal distribution as the number of such variables increases indefinitely. This is because the mu I represents the influence of all explanatory variables that are not explicitly considered in the regression model and influence are small or at least random. B. Even if the number of variables is not large and not strictly dependent, their sum can still be normally distributed. C. The normal distribution is a comparatively simple distribution that includes only two parameters, mean and variance. D. The OLS estimator's probability distributions can be derived easily since the property of normal distribution is that any linear function of normally distributed variables is itself normally distributed. Regression through the origin. This is a situation whereby the constant or intercept beta 1 in the regression model is absent. There are cases when the regression equation or model of two variables appears in this form: yi is equal to beta 2 xi plus mu I. In this model, the intercept or constant is 0 or absent, which indicates that the regression is through the origin. An example of a case where the intercept could be said to be 0 is in the Keynesian income hypothesis, in which consumption could be said to be dependent solely on disposable income. Ci is equal to beta 2 yi plus mu I, equation 48. Here the intercept, which is also called the autonomous income, that is, the income one gets not necessarily engaged in economic activity, sometimes called income received, is absent of 0. Therefore, the regression line will pass through the origin, as shown. The sample regression function of the regression line that passes through the origin is yi estimator is equal to beta 2 estimator xi plus mu I estimator, equation 49. Applying the OLS method, the following formula is obtained for beta 2 and its variance. Let's minimize with respect to the equations below. Differentiate with respect to beta 2 estimator, you get also the equation below. Setting it equal to 0 and simplifying, beta 2 estimator is equal to summation xi yi over summation xi squared, equation 51. Substituting yi is equal to beta 2 xi plus mu I population regression function into the equation, you then get the equation that follow. Setting it equal to 0 and simplifying, beta 2 estimator is equal to summation xi yi over summation xi squared, equation 51. Substituting yi equal to beta 2 xi plus mu I population regression function into the equation, you will then obtain the equation below. Note that E into bracket beta 2 estimator is equal to beta 2. Therefore, E into bracket beta 2 estimator minus beta 2 squared is equal to E parenthesis open summation xi mu I over summation xi squared parenthesis closed squared, equation 53. Expanding the right hand side and noting that the xi is non-stochastic while mu I are homoscedastic and uncorrelated, then we have the equation below, where variance is equal to summation ui estimator squared over n minus 1, equation 55. If we compare this formula with what we obtained for the inclusion of intercept 10, which were written below, the difference between them is that in the model without intercept, we use the raw sums of squares and cross products, but with the presence of the intercept, we use the adjusted from mean sums of squares and cross products. While the degree of freedom, df, for computing variance in the intercept model is n minus 1, it is n minus 2 in the model with intercepts. Method of maximum likelihood, ML estimation. This is a point estimation method that is stronger in some theoretical properties than the OLS method. Let's assume a two-variable model in the formula below. The yi that are normally and independently distributed with mean is beta 1 plus beta 2 x1, and variance is rho squared. Because of this, the joint probability density function PDF of yi, y2 yn of the preceding mean and variance is given as the equation below. However, based on the independence of the y's, this joint probability density function could be written as a product of n individual density function as the formula below, where f of yi is equal to 1 over rho square root of 2 pi exponential brace open minus 1 over 2 into bracket yi minus beta 1 minus beta 2 xi squared over variance brace close. Equation 57. Equation 57 is the density function of a normally distributed variable with the given mean and variance, where exp means that L is raised to the power of the expression indicated in braces. Substitute equation 57 in each of equation 56. We obtain the formula below. If y1, y2, yn are known, while beta 1, beta 2, and variance are unknown, equation 58 is called a likelihood function. This is denoted by LF into bracket beta 1, beta 2 variance, and is written as the equation below. If beta 1, beta 2, and variance are known, but the yi are unknown, then equation 59 is the joint probability density function. That is, the probability of jointly observing the y. This method of maximum likelihood entails the estimation of the unknown parameters such that the probability of observing the given y's is as high or maximum as possible. Thus, we have to obtain the maximum function if equation 59. Let's express equation 59 in log term, that is, in natural log, as written below. Differentiating equation 60 with respect to beta 1, beta 2, and variance will obtain the formula below. Let's set these equations equal to 0 and let beta 1 mean, beta 2 mean, and variance denote the maximum likelihood estimators. It gives 1 over variance summation yi minus beta 1 mean minus beta 2 mean x1 into bracket is equal to 0. Let's set these equations equal to 0 and let beta 1 mean, beta 2 mean, and variance denote the maximum likelihood estimators, it gives the following equations. Simplify equation 64 and 65. Give the further equation below. This is like the normal equations of the least squares theory we have obtained. Thus, the maximum likelihood ML estimators, the betas mean, are the same with the OLS estimators. Let's substitute the maximum likelihood estimators into equation 66 and simplify to get the maximum likelihood estimator variance as shown below. It can be easily seen that ML estimator is different from the OLS estimator, which is equal to 1 over n minus 2 bracket summation mu I squared, which is an unbiased estimator of, however, the ML estimator of variance is biased, and this magnitude of bias can be easily determined by taking the mathematical expectation of equation 69 on both sides. In the equation below, this means that variance is biased, that is, it is not a true representative of rho squared in small samples. However, as n, the sample size, larger and increases indefinitely, the second term in equation 70, the bias factor tends to be 0. Thus, asymptotically, that is, in a very large sample, variance is unbiased too. Confidence interval for regression coefficient. The estimates of coefficients that have been presented earlier are the point single estimate of the unknown population. However, due to sampling fluctuations, a point estimate might differ from the true value, although in repeated sampling, it mean take 2. Its mean value would equal to the true value, that is, E into brackets beta 2 estimator is equal to beta 2. In econometrics, the reliability of the point estimate depends on the standard error of the estimate. Thus, it is appropriate to construct an interval around the point estimate than to fully rely on the estimate. This interval might be within 2 or 3 standard errors on either side of the point estimate, so that the interval has, say, 95% probability of including the true parameter value. Let's assume that we are interested in showing how close beta 2 estimator is to beta 2. In order to do this, we find two positive numbers where the latter lie between 0 and 1, in the sense that the probability that the random interval beta 2 estimator minus standard deviation, beta 2 estimator plus standard deviation contains the true beta 2 is 1 minus alpha. Symbolically, we have, if such an interval exists, then it is known as confidence interval, while 1 minus alpha is known as the confidence coefficient, and alpha into bracket 0 less than alpha less than 1 represent the level of significance. The endpoint of the confidence interval are known as the confidence limit, also called critical values. Beta 2 estimator minus standard deviation is the lower confidence limit, and beta 2 estimator plus standard deviation is the upper confidence limit. Equation 71 indicates that an interval estimator, in contrast to a point estimator, is an interval constructed in a manner that it has a specified probability 1 minus alpha include within its limit the true value of the parameter. For example, if alpha is equal to 0.05 or 5%, then equation 71 becomes the probability that the random interval shown there includes the true beta 2 is 0.95 or 95%. Thus, the interval estimator gives a range of values within which the true beta 2 lies. The following aspects of interval estimation are important to note. A. That equation 71 does not say that the probability of beta 2 lying between the given limit is 1 minus alpha, since beta 2, although an unknown, is assumed to be some fixed number. Either it lies in the interval or it does not. Equation 71 states that the probability of constructing an interval that contains is 1 minus alpha. B, the interval is a random interval, that is, it will vary from one sample to the next because it is based on beta 2 estimator, which is random. C, equation 71 means that in repeated sampling, the confidence intervals are constructed as many times that 1 minus alpha probability bias, in which, in the long run, on the average, the intervals will enclose in 1 minus alpha of the cases in the true value of the parameter. D, the beta 2 estimator is random as long as it is unknown, but there is a specific numerical value of beta 2 estimator. Then it is not long random but fixed. This means that we cannot make the probabilistic that a given fixed interval includes the true beta 2. In this case, beta 2 is either in the fixed interval or outside it. Thus, the probability is either 1 or 0. The confidence interval for beta 2 and beta 1, based on the assumption that UI is normally distributed, it is also the fact that the OLS estimators, beta 1 estimator and beta 2 estimator, are themselves normally distributed with means and variances given earlier. For example, the variable, according to the equation below, this is a standardized normal variable. Thus, we can use the normal distribution to make probability statements about beta 2 provided the true population variance is known. If variance is known, an important property of a normally distributed variable with mean and variance is that the area under the normal curve between mu plus or minus variance is about 68%. That between the limit mu plus or minus 2 rho is about 95%, and that between mu plus or minus 3 rho is about 99.7%. However, variance is usually known. Take 2. However, variance is usually unknown, while in reality it is determined by the unbiased estimator. Replace rho by variance in equation 72. Then T is equal to beta estimator minus beta 2 over rho's into bracket beta estimator is equal to estimator minus parameter over estimated standard error of estimator, according to the equation below. Standard error of estimator is now the standard error of the estimation. Instead of using the normal distribution, the T distribution can be used to establish a confidence interval for beta 2 as shown in the equation below. The T value at the middle of the double inequality is the T value in equation 73, and T alpha over 2 is the value of T variable obtained from the T distribution for alpha over 2 level of significance and n minus 2 df. This is often called the critical value of T at alpha over 2 level of significance. Let's substitute equation 73 into 74. We obtain the formula below. Rearranging, we obtain further the equation 76. Equation 76 gives 100 into 1 minus alpha % confidence interval for beta 2, which can be shortened as 100 into bracket 1 minus alpha % confidence interval for beta 2. Beta estimator minus T alpha over 2 standard error into bracket beta 1 estimator. Similarly, it is also the case that, according to the equation below, this could be shortened as 100 into bracket 1 minus alpha % confidence interval for beta 1. See equation 79 below. A vital feature of equation 77 and 79 is that In both cases, the width of the confidence interval is proportional to the estimator's standard error, which means that the larger the standard error, the more the width of the confidence interval. In other words, the more the standard error of the estimator, the greater is the uncertainty of estimating the true value of the unknown parameter. Therefore, this standard error of the estimator is usually described as a measure of precision of the estimator, that is, how precisely the estimator measures the true value of the population. Study session summary. In this study session, you examine the estimation of the population regression function on the basis of sample regression function. The method of estimation is the ordinary least square OLS, which was in terms of two variable regression model. We went further to discuss the coefficient of determination, which shows how well a regression line fits the data. Finally, you were exposed to the maximum likelihood estimation, which is a point estimation method that is stronger in some theoretical properties than the OLS method. This is the end of study section 5. Thanks for listening.